Hi, welcome to Lesson 8.2, Equations of Planes. In this lesson, the goal is going to be to determine through investigation with and without technology that the solution points x, y, z in 3-space of a single linear equation in 3 variables form a plane. And also to determine, using properties of a plane, the vector or parametric form. We have already looked at the investigation, which you were to go through yourselves through the textbook. Now I'm just going to consolidate some of the material that you would have learned along the way. Okay, so now you may have noticed that the vector equation of a plane is very similar to the vector equation of a line. But of course, because the planes are in 3 dimensions, we need a second non-parallel direction vector included to add a second dimension to that object. So a line, of course, is 1 dimension, 1 direction. A plane has 2 dimensions and 2 directions. So the vector equation of a plane is in the form vector r equals vector r naught plus s times vector a plus t times vector b. Or otherwise seen as x, y, z equals x naught, y naught, z naught plus s times a1, a2, and a3, which could be a sub x, a sub y, and a sub z, plus t times b1, b2, b3, which of course could be b sub x, b sub y, and b sub z. Vector r naught is a position vector of a specific point on the plane, x, y, z, and a and b are the direction vectors with direction numbers a1, 2, and 3, and b1, 2, and 3 respectively of the plane. So the direction vectors of the plane with those direction numbers. And s and t are parameters, and they are of the real number system. Then once you have the vector equation of the plane, you can then separate all the components and form the parametric equation of the plane, which is just taking all the x values and putting them together, same with the y and the z. Okay, so let's take a look at finding a vector and parametric equation of a plane containing certain points. So, because a plane needs 2 vectors, 2 non-parallel vectors to form the plane, what we're going to do is form 2 vectors through these 3 points. Usually what I like to do is just form the vectors from the same starting point. So I will have vector AB and vector AC. Those would be my 2 direction vectors, direction vector 1 and direction vector 2. So vector AB is -4, 0, and 3. And vector AC is going to be -3, 0, and 0. And so then the form of the vector, I'll write it as x, y, and z. Well, I need to include one of these 3 points so I can state a specific point on the plane. So let's use, I don't know, B for example. So we'll say the position vector would be pointing to 0, 1, and 2. Plus we've got the parameter s with direction vector 1, -4, 0, and 3. And parameter t with direction vector -3, 0, 0. Okay, so there is the vector equation of the plane. And then the parametric equation of the plane, you just take out all the like components. So I have x equals -4s minus 3t, y equals 1 plus 0s plus 0t, so that just is y equals 1, and z is 2 plus 3s, and of course plus 0t. So those are the 3 parametric equations for this plane. Now, equations of planes just like we saw with equations of lines, they are not distinct because I could have used BA and BC for the direction vectors, or CB and CA. Doesn't really matter, and I could have used different points here. Instead of 0, 1, 2, I could have used 1, 1, negative 1, or 4, 1, negative 1 there. So, and also with the direction vectors, I could have used scalar multiples of these also. Okay, so just like lines, equations of planes are not distinct. Okay, so let's take a look here. Why do points A, 2, 3, negative 1, B, 8, 5, negative 5, and C, negative 1, 2, 1 not determine a plane? Well, for a plane to exist, basically, I know generally planes look like basically rectangles, but they of course spread out in all directions, in the two directions of the plane itself, forever and ever. So for a plane to exist, we need two non-parallel vectors in order to be the basis for the plane. If we had a plane and we had two vectors, one like this and then the other one collinear, that vector wouldn't necessarily be distinct because it could be on any angle rotating around that line, around those vectors, those collinear vectors. So there could be, or there would be, infinite possibilities of a plane around two vectors that are collinear. So we can't really do that. So we need two vectors that are non-parallel, non-collinear. Okay? So let's take a look to see about these, the vector between these points, and we'll see if they could be a basis for a plane. So AB, you see 8 minus 2, there's 6. 5 minus 3 is 2. And negative 5 minus negative 1 is negative 4. And I'll use vector AC as my standard. So negative 1 minus 2 is negative 3. 2 minus 3 is negative 1. And 1 minus negative 1 is 2. Okay, so I see, when I investigate these two, I see that vector AB actually equals negative 2 times vector AC. And since these are scalar multiples of each other, therefore the direction vectors and D2 are collinear, therefore they are not a basis for the plane. Okay, so basically imagine a line here, and then this plane could rotate around that line infinite number of times, or with infinite number of degrees of separation between them, and there could be infinite different distinct planes through a line, whereas with a basis, with two non-collinear vectors, thinking maybe of, if you think of it as two pencils, whatever, and a paper lying on top of them, there's only one way that that paper can lie on top of that, of these two basis vectors, whereas this one it could rotate all the way around. So because these two direction vectors are collinear, that means they basically form a line, and therefore they cannot determine a plane. Okay, and let's take a look at this last example here. Explain why the line and this point do not determine a plane. We've got a line here, we've got another point. In order to find the basis of a plane, we need two non-collinear vectors. So ideally, if we had a vector between this point and this point, as long as that vector between the two is not collinear to this vector, then we could define a plane. So let's find out if that is so. Okay, so here's point, I'll say maybe that's point A, point Q. So vector AQ would be 8 minus 4, which is 4. negative 7 minus 9 is negative 16, and 5 minus negative 3 is positive 8. Now let's see if does AQ equal some scalar multiple of the direction vector. Well, if I look at 4, negative 16, and 8, and 1, negative 4, and 2, it appears to me as though AQ equals 4 times direction vector D. So therefore, AQ and direction vector D1 are collinear. Therefore, they cannot determine a plane. Okay, so here are some questions at the bottom of the page for you to try. Please work on the first few in class, at home, and then come to class and finish off the rest of those on next school day. Also, on the class website, there is a program that you can use to illustrate lines and planes in 3 dimensions, so you have more of a visual understanding of those and how they work in space. Okay, well, thank you very much for your attention, and we'll see you in class.